Hi guys, sound check. Okay. Ready? Do you hear me?
Yes.
Oh,
Yeah,
cool.
no.
Okay. So I would like to say it's nice to see you, but considering the circumstances, it's very silly to say that. So I would rather not to. Okay. I would like to keep talking for a while to explain you some formal stuff about the course, and then we will do the real stuff, some math. Well, my original plan was to start with a story. You know, it's a dirty trick. The reason for this story is to connect you with the audience. And when the connection is established, you have one really good benefit. You can transfer all your knowledge directly to your mind, to the mind of the audience. So easy learning, really, true story. So you and me sitting in one room, and all my knowledge are transferred directly to your minds. That's how it was supposed to be doing. But no easy learning now. So we have to suffer. But before start suffering, let me explain a couple of things. So first of all, why are we going to suffer? Well, I hope, well, I think you already noticed my awful accent. So that's the first reason to suffer. So if your ears are bleeding, that's okay. The second thing, algebra is a subject for, well, it was invented to make people suffering. And the third thing, everything here is done by me with extreme sadism and cynicism. So I hope it will be fun. Well, my name is Dima. If you have any questions, you just feel free to ask during the lecture. Now, if you, so attendance, I don't care. So if you're here or not, that's your choice. I mean, if you don't like my lectures and you know a better way for preparing, just do it. So my goal here is to help you to learn. So if you need help, if you want to listen my lectures, if you want to learn something, I'll try my best to help you. So, but if that's not what you want, just feel free to find any other way to do a better job. So, okay. But okay, let me start with some writing. That's how we're going to proceed. The only real rule here is you have to pass the final exam. So if you don't pass, you don't pass. That's the only rule. So now, how do you get your final grade? So the final grade consists of three components. The first one is your homework. There will be a homework assignment for each seminar, and it goes with the weight 0.3. It's your homework. The second part is the written test. It goes with 0.2 weight. And the last part is the final exam. It goes with 0.5 weight. So as you can see, you can attend the final exam and it's enough to pass the course. But I hope the lectures will be interesting enough to attend them. Okay. Each group will have a teaching assistant. I will send all the information via HSE emails. All the homework will be sent via HSE emails. Well, regarding the tests and exams, well, I don't know how we are going to organize the tests and exams, so it's an open question for now, but I will inform you when it will be clear. Okay, so I think more or less all non-mathematical stuff was explained. If you have any questions before we start, just ask if you wish. Okay.
Excuse me, and is there a possibility not to attend the exam to get an exemption?
Could you repeat your or make your mic louder?
Is so automat? Do we have such an option?
No, there is no such an option here.
Okay.
At least I didn't think about this option, so I would rather not to.
Okay. Okay. Thank you.
T is tests or what?
What again?
T is what?
Yes, it's a written test.
Written test. Okay. It will be one written test. Yes.
Yes, only one
Okay.
written test, only one exam, and there will be like 8 or 9 homeworks depending on how many seminars we will have.
Okay.
I don't know. Yeah. Another question? Okay, I think we're ready to start. Okay, algebra. So what are we going to do here? So we're going to study algebraic structures. And today I want to start with the simplest possible structure, which is a group. But before, I want to make several preparations. So suppose X is a set. So you might think of it as a collection of elements. So here I write down X. So all the elements inside this circle, well, suppose it's a circle, it's almost round. So all elements inside here represent the elements in the set, and all elements outside represent elements outside of the set. So what is a binary operation on the set X? So definition, binary operation on a set. So binary operation on a set is a rule, well, formally it's a map from a Cartesian product of X times X to X. What does it mean? It means that it's a rule which takes a pair of elements. So we take 2 elements, say X and Y. They are both elements from X capital. And we take them to a new element, which is denoted by X times Y. Here it means that we produce some new element with the name X times Y. So again, a binary operation is a map.
Sorry.
Yeah.
Is it possible that X by Y will not belong to set X?
No, it's not possible. This notation means that the result always belongs to X. So here, this is the source of your operation, and this is the target of your operation. So the arguments always belong to the source, and the result always belongs to the target. So the result must be inside X in any situation. Okay, so let me give you an example. So an example. The first one, a usual addition of integer numbers. So you have a pair of integer numbers, n times m, and it goes to the usual sum, n plus m. Another example, you can take maximum of two integer numbers. So you're given two integer numbers, and they go to the maximum. And there are a lot of other different operations on the set of integers, and you may produce like 1 million operations, like infinite number of operations on the set of integers or any other infinite set. So, okay, do you have any questions regarding the definition? Okay, just in case, in my examples, there are two different notations for a binary operation. So here you have an operator style notation where the name of the operation goes between the arguments, so n plus m. And here on the right, you have a function style notation where the name of the operation goes before the arguments, and the arguments are passed in brackets, in round brackets. So these are two different forms, so you may use any of them if you like. Okay, now I want to discuss several properties of a binary operation on a set. So there are 4 properties that we care about. So properties. The first one. So here we're given an operation on a set X. And the first property is associativity. So we say that the operation is associative if we don't care about the order of the operations, which means that for any elements X, Y, and Z from your set, just in case, this first symbol, if you're not familiar with it, it means any. So I choose any X, any Y, and any Z from my set X capital. So for any triple of elements, you can compute X times Y and then times Z. Or you may compute the product in the other way. First, you compute Y times Z and then multiply the result by X from the left. So you want these two things to be the same for all inputs, X, Y, and Z. And if this equality holds for each X, Y, and Z, the operation is called associative. So the usual addition of integer numbers is associative, and the subtraction of integer numbers is not associative. Are there any questions? Okay, so the next property, neutral element. We say that an operation has a neutral element. Okay, let's say in a different way. So let E be an element of X. We say that E is a neutral element or identity. These are two different names. If for every element X in X, E times X equals X times E equals X. So a neutral element is such an element that it doesn't change anything when you multiply by this element. So, and just in case, it's important to notice that both equalities are required. So it may happen that E times X equals X, but X times E is not equals E, or the other way around. So you need all the equalities written here. We say, okay, we say that it's a neutral element, well, for the operation. Let's say. I think it doesn't matter which proposition you use. So it's a neutral element for the operation. Okay. So the next property. By the way, do you need an example?
No, I suppose.
Oh, okay. Just in case.
If you give an example of when a times x is not equal to x times e, it would be good.
Okay. So when the property holds for, okay. Let's consider. Oh, sorry, different color. Let's consider the subtraction of integers. So m time mn goes to m minus n. So there is an element which plays the role of the neutral element, of the right neutral element, what I would say. So let's show there is no neutral element here for this operation. So for example, let E be a number from Z which plays the role of the neutral element. Then it must satisfy this property. E minus M equals M, and M minus E equals M. So from this, so there is only one element satisfying the second equality for all possible M. So E must be 0 for the second equality to hold. But as you may notice, there is no such E for the first equality to hold for any M. So this is an example.
Okay, thank you.
Do you have any questions considering the example? Regarding the example? Okay. So actually, well, if you want to find, so if you want to find an example, usually it lies around you. Like just take some familiar operation, consider like subtraction of integers, taking maximum of integers, or like multiplication of real numbers or real numbers without zero. Just play with the known operations and you will always find some counterexamples. Well, I'm looking to the chat. People discuss the example. I just want to clarify. Do you have any questions? Should I clarify something or not?
So do you claim that for this kind of an operation, we don't have a neutral element, right?
Yes, there is no neutral element here because there is no element E satisfying the first equality for all possible M. Because from the, should I explain that, why there is no such an element?
No, it's pretty clear. You just proved it.
Yeah, okay, yeah, it should be clear. I mean, but just in case, because I see that there is a conversation here in the chat. So if you need my help, just feel free to ask a question. Okay, let's proceed. So the next property. So the third property, the existence of an inverse element. So one important remark before we start. This is, so the previous two properties were independent ones. So you may pull this property on any operation, but this property is dependent on the previous one. So suppose that we have an operation with a neutral element. Oh, by the way, I'm sorry. I forgot to mention one thing regarding a neutral element. if a neutral element exists, so the important question, how many neutral elements do we have in general? So how many neutral elements do we have?
The only one?
0 or 1. So,
Why it's
So,
not
for
possible to
example,
have
before we may have no
neutral
neutral
elements?
yeah. Again, a question?
Why it's not possible to have more than one neutral
I will
elements?
explain. I will
For
explain.
example, can I give an example? For example, we consider integer operation in integer that doesn't change it. So any element will be neutral element by this operation
Which operation do you mean?
that doesn't change integer. For example, integer by this operation integer will be equal to the first integer.
So you're not presenting me an operation. Operation is a rule which takes two integers and gives you an integer result. What is your operation?
It's give you the first integer, for example.
But yeah, but then there is no neutral element because so okay. In your example, you take the product to the first element, but then so let's denote it by circle. So you want to find an element with this property. Yep. But by your definition,
I understand. Yes, it's impossible.
yeah. So let me explain how many elements, neutral elements do we have. So the answer is there is at most one neutral element. So at most one. So let me show why. So suppose we have two neutral elements. So E1 and E2 are two neutral elements. Then consider this product, E1 times E2.
Yes.
Then from one hand side, E1 is neutral element. It means that E1 times anything is equal to this anything. So this must be E2 because E1 is the neutral element. So this holds because E1 is neutral. But in the similar way, since E2 is neutral, then X times E2 is equal to X. So this must be E1. So that's why if you're given two neutral elements, E1 and E2, they are the same. Is it clear? Do you have any questions? Okay, so now I'm ready to proceed. So to the next property. The third property. So suppose we are given an operation with a neutral element, and E and X is a neutral element or identity. So if you do not have a neutral element for your operation, it is impossible to pose this property. So it is impossible to check it. I mean, it doesn't make sense without existence of a neutral element. So now, if X is a given element of X, then we say that Y is an inverse element, inverse to X, if X times Y equals neutral element and Y times X equals neutral element. So in this case, we say that Y is inverse to X. That's the definition. For example, if you have an integer addition, then the neutral element is 0. It's neutral element. And if you're given an element m, then what are the inverse elements? So minus m is the only inverse element for a given m, because m plus minus m equals 0 and minus m plus m equals 0. So this is an example of an inverse element. And again, a natural question is, how many inverse elements do we have for a given element x? And the answer is at most 1. So how many inverse elements do we have? Well, I mean, for a particular element x. And the answer, at most 1. I will explain why again. So suppose we're given 2 inverse elements. So y1 and y2 are inverse elements for a given element x. What does it mean? It means that x times y1 equals neutral element and y1 times x equals neutral element. This means that y1 is an inverse element, and we have the same pair of equations for y2. So now I want to show you that from these 4 equalities, we derive that y1 equals to y2. Okay. Just give me a second. But let me formulate a claim before we proceed. I'm sorry for that, but I think it's better to formulate this statement as a claim to list all the required axioms to prove this statement, because otherwise it will be a mess. So I'm sorry for doing that, but let's prove a claim. Suppose that we're given an operation with 2 properties. First, this operation is associative. And the second, it has a neutral element. There exists E and X, a neutral element. Then, for any element X, there is at most 1 inverse element. This is the claim that I want to prove. Just in case, this symbol means any, this symbol means exists, and the exclamation mark means unique.
And is it possible that there is no inverse element in this case?
Yeah, it's possible. I'll give you an example in a
Yeah.
moment. But first, let me show you that there is at most 1, and then I will go.
For example, we have sets that consist of only 1 element.
But yeah, no, when set consists of 1 element, and this element must be neutral, and the inverse for the neutral element is neutral element.
Okay, yes, two elements, for example.
What again?
Not 1, but 2 elements. 1 and 0, for example.
But it depends on the operation. It may.
Just the usual operation with integers, but we have only 1 and 0.
But which operation?
Plus, minus, multiplication.
Well, multiplication works in this case. The 0 element will not have an inverse. So just take all integers and take multiplication. Then the neutral element is 1, and there is no inverse for 0 element or any element different from plus minus 1. So, okay, let me prove the claim. So we have, again, so suppose we have 2 inverse elements. Now, consider the following expression: y1 times x times y2. We may put brackets in two different ways. So first of all, we may compute this product and then the other one, or we may compute it in the other way around, like in this way. So here we use that the operation is associative, so it doesn't matter which order of computation we choose. But now, since y1 times x is the neutral element, the result here is e times y2, and since e is the neutral element, the result is y2. In a similar way, the right-hand side is equal to y1 times e, and the result is y1. So if your operation is associative, there is only at most one inverse element. So any two inverse elements are the same, if they exist. So do you have any questions here? Okay, so for completeness, an example when there is no inverse element, so take the usual integer numbers with usual multiplication. So then the neutral element is 1. This is your neutral element. It doesn't change anything by multiplication. And the inverse element for 1 is 1. For -1, the inverse element is -1. And there is no inverse element for any other one. So if your number is not plus minus 1, so there is no inverse. So this is an example where you have no inverse element for some elements. Okay. Yep.
No, it's okay. We're in whole numbers.
Okay. So, and since we have at most one inverse element, we have a special notation for this inverse element. So actually, there are two different notations. I will discuss them later, but now I want to give you just one of them. So if y is inverse to x, then we denote y by x to the power -1. So this is how we simply say that y is an inverse to x. We just simply write x to the power x -1. Then the rules for multiplication becomes like this. So just remember that x to the power -1 simply means that this element is inverse, which means that these two equations hold. Okay, we're going next. And the last property is this, the property number 4. We say that this operation is commutative oh boy. So if the order of arguments doesn't matter, which means for any elements x and y from x, you may multiply x and y in this order, and you multiply x and y in the other order. The result must be the same. So if the order of the operations doesn't matter, then the operation is called commutative. So integer addition is commutative. So it's commutative. And integer subtraction is not commutative. Okay, these are 4 important properties which we will use later.
Sorry for interrupting, but I have a question about previous notation with x in power of -1.
Yep.
My question is, on the same set we can have a lot of different binary operations, and it is not always convenient. For example, if we write x which belongs to the real.
I see the question. So we have 2 different notations for the for different operations.
Yeah.
Well, yeah, it may lead to confusion, but usually we set notation. Well, usually we will discuss a set with one operation, with one good operation. So it will lead to no confusion. But in every case where we have several operations, it will be clear what we mean. So you will see. So,
Okay.
so for now, we just think of one operation.
Okay, thank you.
Mm-hmm. Okay, so now I'm going to define one of the most important objects in algebra, which is group. So, but before giving you a definition, I want to clarify a structure, the structure of any definition in algebra. So, definition in algebra. So when we define a new object in algebra, the definition consists of two parts. So every definition consists of two parts. The first part describes the data required for the definition. And the second part describes the axioms the data must satisfy. So every time I give you a definition of an algebraic structure or algebraic object, I will give the definition. So I will split the definition in two parts. So the first part consists of the data, and the second part consists of the axioms. So now I want to define a group. So the definition will follow this pattern. So definition, group. So first, we need to set the data. So to define a group, we must fix two things. The first thing, G, is an arbitrary set. The second data is an operation on the set G. So we fix these two things. Now, the second part is the axioms. We must satisfy three axioms. So the first axiom, the operation must be associative. The second, the operation must have a neutral element. There exists a neutral element for this operation. And the third axiom, every element must be invertible, which means every element has an inverse. For every element x in G, there exists an inverse element. An inverse x to the power minus 1. So let me repeat the definition. So here we define a group, let me say, which is a pair G and a set G and an operation. So these are two pieces of data we need to fix. And then this operation must be good in the sense that it must be associative, it has neutral element, and each element is invertible, including the neutral element. So this pair G and an operation satisfying these three axioms is called a group. Do you have any questions regarding the definition? Okay, so let me give you an example of a group. So, and by the way, before we proceed to an example, I just want to give you a fourth property. If additionally, so I will write it with a blue color, if additionally the operation is commutative, we say that this group is abelian. Or commutative. So if we have these three axioms and this additional axiom, then this is just an abelian group. So in abelian group, the order of elements doesn't matter, or commutative group. Abelian, well, if you don't know the term, it's in Russian, it's Abeleva группа, yes. Well, it's called in honor of a mathematician that's come from his surname, Abel. So, okay, let me give you an example. Example number one. Well, integers with addition is a group. Second, integers with multiplication is not a group. Next, let me recall you the operations modulo some natural number. So suppose we fix some natural number, well, non-zero natural number. Then we have a finite set of natural numbers strictly smaller than n. And here we have operation, which is addition modular n. That is Zn times Zn goes to Zn. And we denote this operation by the usual addition notation. So the pair of, n is already occupied. So A, B goes to A plus B modulo n, which means you find the sum of the elements A and B, and then take the remainder with respect to n, while you divide by n. Okay. Is this example clear? I mean, do you have any questions regarding this example?
Yes, it is not clear why multiplication on integer numbers is not a group. Yeah,
Because not every element is invertible. For example, 0 is not invertible. That was mentioned earlier.
And
Excuse me.
what is?
Yep.
Go ahead.
I just wanted to ask whether we first do the modular operation with B and then sum it with A, or no?
No, we find the sum of A and B. Since A and B are less than n, it doesn't make sense to make modular operation on B, because it's already smaller than n.
Because just without braces wasn't as clear. Okay, thank you.
Okay.
And
So,
also, the third example, what does it illustrate? I didn't catch that.
Yeah, that's a good question. So this pair is a group. So I will leave the explanation for the seminars, but just in case, the neutral element here is 0, and the inverse element for A is n minus A. So, but I will leave this for the seminar. And the fourth example, let's consider Zn star, which is the set of all integers from Zn, which are co-prime with n. So K is a number from 0 to n minus 1, which has no common factors with n. And then this set with multiplication, with modular multiplication, so A, B goes to A times B mod n, is also a group. It's not pretty obvious, but we will explain this during the seminars.
Я тебе разрешаю, если что.
Guys, okay, let's proceed. Okay, there are two different, what happened? Yeah, so I gave you a definition of a group. I gave you several examples, and now I want to discuss two different notations for the group operations. So usually it's inconvenient to write circle all the time, so we will simply use two different notations: multiplicative notations and additive notation. In multiplicative notation, we denote our multiplication as the usual multiplication of numbers. So the result is simply xy. So we just omit the operation here. And in the additive notation, we use symbol plus and use, so the operation, the result of the operation is x plus y. In this case, neutral element is denoted by 1. In additive case, the neutral element is denoted by 0. In multiplicative notation, the inverse element is denoted by x to the power minus 1. And in the additive notation, the inverse element is denoted by minus x. And also, if we want to take a power of elements, so if we want to multiply several elements, so here we denote it by a power of element. And in the additive notation, if we take sum of several elements, we denote it as a multiple with a natural number n. So here we have n elements, and here we have n elements. So these are just two different notations for the operation. So you may use any of them. Okay. Do you have any questions regarding what I've said here?
No.
Okay. So just in case, so this is called a power of element. So this is also a power of element, but in an additive notation. So do not confuse these things with usual addition and multiplication, for example, of integer numbers, because here G is an arbitrary set. There is no natural addition and multiplication. So this is just a new name for your operation. So which name you use, it's just your choice. It's just for convenience. So instead of writing a circle and e each time, I just use usual multiplication and number 1 to denote well, multiplication and the neutral element. And here I just use zero element. Yes, someone wants any question? I've seen a hand in the chat. Okay. So let me proceed. Now, I want to discuss subgroups. So suppose we're given a group G. So definition. So G is a group. Yeah, by the way, earlier I said that group must be a pair, a set G and an operation. But by use of notation, we usually omit the name of the operation and say that just G is a group. Here we just assume that G has some operation which obey all the required axioms. So we just simply say that G is a group. So now I want to define a subgroup of G. So I will say that H in G is a subgroup so this is what I want to define. What does it mean that H is a subgroup of G? So as earlier, first of all, I should specify the data. So H must be a subset. So I just take some elements from the group G. And now x cells. So I will use multiplicative notation. So the neutral element must be inside H. The next property, oops. The next property, if I take two elements from H, their product must be in H. And the third property, if I take an element from H, its inverse must be in H. So let me show you the definition. So if you are given a subset of a group which satisfies these three properties, it's called a subgroup. So subgroup must contain the neutral element, it must be closed under multiplication, and it must be closed under the operation of taking the inverse element. Do you have any questions regarding the definition? Okay. Just in case, there are two examples. If I take integer numbers with addition, then consider H to be the set of even numbers, which I'll denote by 2 times z. Then this is a subgroup. And if I consider the set of odd numbers, which is 1 plus 2z, this is not a subgroup. Well, why this in the second case, why H is not a subgroup? Well, because, for example, the neutral element is not inside H. For example, there is no 0 in H, because 0 element is the neutral element for this group Z with the operation plus. And you can check all the properties for the first example. Okay, now I want to discuss some properties of elements in a group. So I want to discuss cyclic groups, cyclic subgroups. So if you're given an element, you can always generate a subgroup by this element. But before doing that, I want to prove several properties, formal properties, which helps you a lot. So let me formulate a claim. Suppose G is a group. Now, the following three properties hold. The first one, for any two elements x and y in G, x times y inverse equals y inverse x inverse. Second, for any element x and G, x inverse to the power of n is the same thing as x to the power of n and then inverse. And the third property, if you take any element x, then x to the n times, oh, I forgot to define this notation. Okay, I'll write down the property and then define the notation. Is equal to whenever n and m are integers. So it's clear what it means for positive integers, but I want to clarify the meaning of this notation x to the power of n for any integer. I'm sorry for being messy. So, okay, so here x to the power of n means x times x.
Sorry, we cannot hear you. It's on my problem.
Again?
No, it's fine. We can hear.
Oh, there was a problem with the voice. So here is the definition in general case. So x to the power of n, if n is positive, means that you multiply x n times. If n is 0, then it means that x to the power of 0 is the neutral element. And if n is negative, it means that you multiply minus n times the inverse element of x. So this is the full notation. So, in this equality, I mean n and m could be any integer numbers, positive, negative, or 0. Okay. So this is the claim I want to prove. Do you think should we prove it, or it's clear? Okay. Okay, I see. Let's start with the first property. Okay, the property number 1. So we want to prove this. So the first question is how to prove such an equality. So you see here, what we are saying here is that the right-hand side is the inverse element for the element xy. Since the inverse, so this guy is the inverse element for this one, but the inverse element is unique. So how to prove that this equality holds? We should prove that the right-hand side satisfies property of the inverse element, which means we should prove that this equality holds. And this equality holds. If we prove this, then it simply means that this element is the inverse and the equality holds. But now it's clear, we just cancel this and this. How to compute this? So x, y inverse, x inverse, we don't care about the brackets because the operation is associative. So this product is equal to 1, so just this thing. If you will multiply by the neutral element, nothing is changed. So this thing, and when we multiply this, it's the neutral element. So this is how it's proved. The other equality is should be proven in the similar way. So that's the first property. So I'm going to, if you don't have questions, I will proceed to the second one. So the second one was this one. So taking the inverse and taking a power, these two operations commute. So, well, we want to prove that this thing is the same as this thing. Well, formally, we should consider 3 cases. N is greater than 0, n is equal to 0, and n is negative. So I will consider just one simple case because all the other cases are more or less the same. So again, so what we do here, let's consider this thing. Let's G1, Gn be arbitrary elements of the group G. So I want to consider G1, Gn to the power of -1. So applying the previous rule n times, we see that this is the product of G1, Gn in the opposite direction. So is it clear how it follows from the first property, from the first item of the claim? Do you have any questions regarding that? Okay, but now just simply substitute G1 equals x, etc., Gn equals x. Then you will get x to the n inverse equals x minus 1 to the n in case n is greater than 0. That's how it proved for the case n is greater than 0. if you prove it for the case, okay, now, in case n being 0, that's clear because the left-hand side is the identity element, because any element to the power of 0 is the identity element. And this guy is the identity element, and the inverse for the identity element is the identity element. So for n being 0, it's clear. Should I write this down, or we may skip it? Okay. 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 Someone wants to write this down. So in case n being 0, we write x to the 0 to the minus 1 is the same thing as 1 to the minus 1, and this is the same thing as 1. And in this case, every element to the power of 0 is 1, just by definition. So this is the same thing. Okay? And now we want to prove this for negative n. So let n be negative. So now, what is n x to the power of n? It's simply okay, let me switch the notation for simplicity. I'll take d to be minus n. So here we consider x to the power of minus d. Okay, this will be simpler for me, and I hope for you also. So now we want to compute this to the power of minus 1. So again, by definition, what I have inside is x to the power minus 1, etc., x to the power minus 1 d times, and then we want to take the inverse. Okay? And then, using the rule from the previous item, is the same thing as x minus 1 to the in the opposite order. But if we take inverse element to the inverse element, it will be the same element x, just by definition. So this will be x to the power of d. So the left-hand side is equal to x to the power of d. Are there any questions regarding this computation? Okay. The second thing we need to compute is x inverse to the power minus d. So again, by definition, what it means, when I raise to the negative power, I should take the element x minus 1, take its inverse, and multiply it d times. So this simply means I take x minus 1, takes its inverse, and multiply it d times. This is just by definition. And again, using the same rule as before, or even using this equality, we see that both expressions are the same. Well, if you are lost, it's probably okay, because all these formal computations are not very easy at the first time. But I will write lecture notes where everything will be written. So even if you don't have your own notes, it will be easier to follow or to repeat all the computations. So I believe we proved this. Excuse me, minus d. No, here d is positive. I specifically switched the notation in such a way that d denotes a positive number. So, okay. So we're done here. Okay, now let me define, oh God. So let me define a cyclic group. Oh, come on. What? Whiteboard. Okay. So, yeah. Oh, that's nice. Someone is sleeping. I think it's a success. Yeah. How do you know that your lecture is great? Well, when people are sleeping, it means a complete success. I hope you agree with me. Okay. Yep. He's definitely enjoying the lecture. Okay. So now, suppose we are given a group G. G small is an element, just arbitrary element. I will denote by G in angles the set of all possible integer powers of the element G, which is 1, G, G to the 2, etc., G to the n, etc., and here G inverse, G minus 2, etc. So just G to the n is any integer number. So this is a subset in a group G. So now it's easy to verify that this subset is a subgroup. So this subset is a subgroup. I skip this verification, we will check it during the seminar session. But what is important is the definition. So this subgroup is called the cyclic subgroup generated by the element G. So the definition, G is the cyclic subgroup generated by the element G. And the element G is called a generator. Okay. Well, if the so next definition, if there exists an element G such that its cyclic subgroup is equal to the whole group G, then the group G is called cyclic. Then G is a cyclic group. And there are two. So are there any questions regarding the definition? Okay.
I have a question. Do we have some kind of way to pick G, or is it like kind of random and exist on its own?
Again, just
is there some way to like find this G, or it just exists?
Oh,
way?
for the second definition. Yeah, it just exists.
Generator. Okay.
Yeah, it just exists. So, well, in a specific case, when you're given a specific group G, of course, there is a way to find such a generator, and that's a good problem to exercise. But in general, we just pose the condition that there must be an element G small that the whole group coincide with its cyclic subgroup. Yep. In Russian, it's called порождена элементом. Okay. So So there are several examples of a cyclic group. For example, if you take the group Z with addition, then element 1, a subgroup generated by the element 1, well, in additive notation, which means 0, 1, 2, etc., -1, and so on, inside with the whole group. And also the element -1 generate this subgroup, or this group, Z. So this is an example of a cyclic group. Another example of a cyclic group is Zn with an addition. Here the element 1 also is a generator for this group. These are examples of a cyclic group. And an example of a non-cyclic group, for example, all real numbers with addition is not cyclic. And there are a lot of other examples of non-cyclic groups. If there are no questions, I'll proceed. Now, I want to describe the structure of an arbitrary cyclic group, and probably I'll have enough, or close to that. I have enough time to explain this. So, the claim. Suppose G is a group, and G small is an arbitrary element. Then there are two options for its powers. The option number 1, all the powers are different. So for any n and m distinct integer numbers, g to the n is not equal to g to the m. That's the first option. And the second option, there exists n positive natural number such that powers from 0 to n minus 1 are distinct, and g to the n equals 1. So these are two options, actually. There are no other options. So what this claim means, it means that here in the definition of, oh, not here, just I want to show you everything at the same time. So here, your cyclic subgroup consists of all possible integer powers of the element G. So the claim says either all these elements are different or they are repeated in cycles. So there is a block of n elements where all powers are different, and then this block is repeated to the left and to the right infinitely many times. So that's how your cyclic subgroup looks like in general. Okay. Let me prove this, and probably, okay, we have 5 minutes. We have 5 minutes. So, by the way, do you have any questions regarding the claim and regarding the statement?
And can you go to the previous statements or examples? What is Zn1? Yeah, this one. What is it?
Oh,
it is plus. Oh my God. Okay.
Yeah, it's plus.
Sorry.
So you have all the numbers from 0 to n minus 1 with addition modular n, and this group is cyclic. It's generated by the element 1.
Yeah. Okay. Thank you.
Okay. Okay. So, well, in order to prove this, we must show that in case when at least 2 powers are the same, then we have the second option. Okay. So if all the powers are different, then we have the option 1, but suppose that there are two powers which are the same. Then we'll multiply both the right-hand side and the left-hand side by g to the minus m, and we will get g to the n minus m is 1. So this implies this. So we may assume that we have an equality like this. But now n is, yeah, and here n and m were different. So here n and m were different. So here n minus 1 is not 0. So we may assume that we have this equality and n is either greater than 0 or smaller than 0. If n is smaller than 0, we multiply both sides by g to the minus n. And we may assume that n is greater than 0. So if this holds for some distinct n and m, there is a positive integer n such that g to the n equals 1. That's the first claim. That's what we have shown here. So now consider the smallest possible, so let d be the smallest positive number such that g to the d is 1. So I claim that all the elements 1, g, and so on, g to the d minus 1 are distinct. If I prove that, then we're done. Because, well, due to this equality, we have this repetition in cycles for all other powers. But the only thing that we're missing is to show that these powers are distinct. But now, suppose this is wrong. So there is some g to the k from here and g to the s from here, which are the same. And we assume that s is greater than k. Then multiplying by g to the minus k, multiplying by g to the minus k, this equality, we get g to the s minus k is equal to 1, and then s minus k is greater than 0 because s and k were distinct, and it's strictly smaller than d because s and k were strictly smaller than d. So we found a smaller number, s minus k, such that g to this power is equal to 1, which is a contradiction to the choice of d. This contradicts to the choice of d. That's, so where did we get it? This contradiction, we get it from this assumption that there were two elements, g to the k and g to the s, which were the same. So, okay, I think we proved the claim. And now I want to conclude with the final definition. We will need it for the seminar session. So, okay, so if we're given, so definition, if we're given an element G from a group G, then what is the order of this element? So this is the smallest possible positive, this is the smallest positive number, so it's a positive integer number such that g to the n is equal to 1. Or if there is no such a number, it's called infinity if there is no such n that g to the n equals 1. So the smallest positive number such that g to the n is equal to 1 is called the order of the element. And what we have proven here, that the order of G is equal to the number of elements in the cyclic subgroup generated by this element. Okay, we're out of time, but this is pretty much everything I wanted to explain during this lecture. Okay, I hope you enjoyed the process, and I hope I'll see at least a half of you the next time.
Can I ask another question?
Yeah. Okay.
Do we have some kind of lecture notes?
Yeah. I'll post the lecture notes on the wiki page, so everything will be there. And also, this whiteboard will be posted with the lecture notes, so you will be able to read all of them. So don't worry. And I will send all the instructions via email on the HSE official emails. Okay, do you have any other questions? Yeah, we will have seminars. So the first group will attend the seminar in a couple of minutes, will meet with me, and the other groups will have seminars the other days. I don't remember exactly the timetable, but okay. Okay, I'll send you the information regarding the seminars in the other groups today. So
sorry, where will be our seminar today, Samin?
The group, the first group will have seminar.
I mean, in this Zoom, or will use another link?
There is the other link. There is the other link. It must be in the timetable, but if you don't have it, I'll send it to you. Okay, let me stop the demonstration, and I'll send you the link, and we have to stop in a minute. Just give me 1 second. Here is the link for the first group, and the other groups will have seminar the other days. So I'll send you the email with all the information, just in case, if you don't have this information. Yeah. Okay, thank you, guys. We should stop.
Thank you.
See you next time.
See you in 5 minutes.